Okay, hi again. I'm Fabio, and I'm part of the Parallel Universe team as a software developer, as you know. We build a unique open source JVM stack to write better and more efficient concurrent, scalable, and fault-tolerant applications. First of all, thanks for coming, and thanks to the JetBrains guys for organizing this session, as well as for providing the development community with a lot of excellent tools like IDEA and Kotlin, which we're going to use. We'll go through an example application in this session, several versions of it, and the code, well, you can reach it at this GitHub repository. There are several versions you can reach through the release. There are actually more versions that we're going to see today for your playing pleasure afterwards. And okay, so, well, I'd like to start with what we are talking today. We are talking about Quasar and Fibers. So Quasar is an open source library for the JVM that gives you several things, several useful concurrent abstractions, but most prominently fibers. So what are fibers? Fibers are just like threads, except you can have millions of them rather than just a few thousand threads. And they're very cheap to block. So this typically means that, unlike threads, you don't need to worry about creating too many fibers. Just one small thing I was forgetting. Well, if you have any questions, we'll make pauses during the presentation, during the session. So I will just stop and ask you if you have any questions. We can answer them during the talk. So, well, first, let's have a look. Let's start with a simple text-based application that is using regular threads to retrieve some stock information. I'd like to go through the code so that we can also get familiar with some Kotlin constructs. Well, the first thing you can see is that semicolons are optional in Kotlin. So basically, well, those are a few keystrokes spared, which is always a nice thing. Kotlin supports import bindings, and you can use the same keyword, import keyword, for all sorts of entities, packages, classes, objects, whatnot. So, well, the first business model class we're going to look at is stock, of course. It's a Kotlin class, and you can see that Kotlin's primary constructor is part of the class header and can specify val or var to create corresponding mutable or immutable properties, respectively. So you don't have to write boring boilerplate assignments just to copy the constructor parameters into properties. By default, Kotlin classes and methods, they are closed for extension, which is a very wise best practice by default, and they can be made inheritable or overridable through the open keyword. So another feature we're going to use is singletons. Well, literal objects, actually. Kotlin supports the singleton pattern directly as a literal objects. And actually, this one that you see here, this companion object, is just a special case of a literal object that can be referred through the enclosing class identifier. So it uses the same name as the enclosing class. Companion objects, well, they can replace Java static features, but they are much more than that because they are really full-blown objects, so they can inherit, implement, and define properties and methods. You won't see a lot of types in this session. It doesn't mean that Kotlin is weakly typed. Kotlin is actually very strongly typed, but it has extensive type inference. So most of the types are inferred by the compiler. There's no new keyword. It's not really needed, so it's not in Kotlin. Constructors are just called simply through the class name. And well, let's have a look at the first business method here. First of all, we have to find a stock by name, right? So currently we have a very simple implementation. We're not just interested in this. It just constructs and caches stock objects. But a few Kotlin features are interesting here. Methods can be defined as a single expression rather than a block. So this is very useful in functional style. And method parameters can also have default values, like in this case, name. The name parameter will use Goog as default if no value is provided during the call. Of course, Kotlin supports higher order functions. If the last parameter of an higher order function like this one, get or put, which is part of the Kotlin standard library, if the last parameter is a function, in this case it is a lambda or a function literal, there is this nice syntax you can use. You don't need to include the lambda in the arguments, and it's very DSL-like. And in this case, actually, we only have one parameter. In this, we don't even need to mention it in the parameter list. It can be simply referred to as it. I'm not really using it here because it is unit, so it's not of much use in this case. We're going to keep a sliding window for historical data because we're going to provide a historical average of the stock. And we're going to initialize it in this init block. So, well, Kotlin classes can have more than one constructor. There is one main constructor, there can be others that can refer to the main one. But if you don't need more constructors, you can just use an init block. So in this case, we are using an iteration over a dynamic range to fill the historical data with some random values. And the random values are provided by the new val function. Of course, well, Kotlin has visibility modifiers. They are quite similar to the Java ones. Well, many Kotlin constructs, like, for example, if that we are using here, they can be used both as statements and as expressions. So in this case, we are using an if construct as an expression, just to provide a value to the value constructor. And well, locals can be mutable or immutable too, so this is quite important in functional programming. But I would say in general to control the scope of your mutability so that you can limit side effects. Well, then we have another few business methods. We can retrieve the current stock value. In this case, I'm defining the method body as a block, so return is really mandatory. Advice, to get some advice about the stock. Should we buy more? Should we sell? Should we keep it? And finally, the historical average, which is implemented in a very traditional imperative fashion in this case. So we have mutable variable sum accumulating over the historical data, and then we divide by the size, and we return the result. We have another couple of business model classes. So we have value. Value is a data class, and data classes are very useful in Kotlin to define value models because Kotlin will generate the string equals hash code and a nice copy method that you can use to copy your value. And you can also optionally pass in parameters named after the properties to replace selectively the single properties of your value during the copy. We also can use enumeration classes. Actually, enumeration classes in Kotlin are pretty much full-featured classes, and the enumeration literals are really literal object instances of the enumeration class. So, well, you can do with them really whatever you want, whatever you normally do with objects and classes. So, we are finally looking at the main method. So what is our program doing? It's basically asking the user for the stock name, and I'm using the readLine standard library function here. The readLine standard library function returns an optional string. Actually, this is a nullable type. Because if we interrupt the input, we can get a null. Kotlin anyway aims at eliminating null pointer exceptions, and to this end, it has nullable and non-nullable types, as well as platform types for the values that are produced by Java code. A nullable reference type is suffixed by a question mark, like you see here. I'm declaring it explicitly so that you can see it more easily. And well, so we can get from the user on the standard input some string to look for, but we can also get nothing. So, well, before performing the search with stock find, we should really check if we got something or not. And if we got nothing, well, we just return a default value that has type string, non-nullable, of course. If we got something, we can just return the previous identifier, so as name maybe. Why is that? This is because in this else branch, Kotlin will automatically cast a string maybe or option string nullable to string non-nullable. And this actually works only with immutables because, of course, if you have mutables, they can be changed after the check. Actually, you see this yellow suggestion by IDEA. IDEA is suggesting to replace these verbose if expression with something much shorter, which is the avis expression, which we can use in these cases when testing for now. Well, it asks if I want to align the local variable. There is just one occurrence, why not? Right, okay, so we are set here. The find method, in the general case, it can really return nothing because maybe it can't find the stock we are looking for. In our implementation, this is not really happening, so we're not worrying too much about this. Well, in the general case, this can happen. So what we are doing here is exactly the same thing. So in order to have for sure a stock, we check against now, and if it is now, we return a default, which is defined by, as a companion object property, by the way. And of course, we have the same suggestion here by IDEA, so we'll just follow it. And oh, that's it, with some more indentation. This is very compact and quite readable too. Also, I'm using named parameters here. So I'm calling the find method by naming explicitly the parameter. This is another of Kotlin's features. Okay, so now we'll use threads and channels to retrieve the stock information concurrently. So we got a stock in our hands, and with the stock we can retrieve 3 pieces of information. So the average, the current value, and the advice for the stock. There is no dependency between these 3 values, so we can actually retrieve this information concurrently. What about Quasar channels? Quasar channels, they are just like Go channels. In this case, we're using channels without buffer, so they synchronize producers and consumers. Channels with buffers decouple them up to the buffer size, of course. So when the buffer is full, the channel can be configured to throw an exception, to drop the lowest value, or just to block, so synchronizing producers and consumers again. And channels can also be created to accept multiple consumers and or producers. Of course, we are going to use channels with the threads. So Quasar channels work with any type of strand. Quasar has this strand abstraction that gives a common interface to fibers and to threads, and channels can work with both of them, as we'll see. A few words about threads. What are threads? Threads are actually, well, they are an abstraction, right? So threads are an imperative abstraction. They are virtual sequential machines that execute a body of actions, and they can be spawned from other threads. They can also be joined by other threads or fibers, for that matter. So joined means really awaited for termination. So we wait for them to terminate because we have some dependency on the result, for example. So in this case, we use the thread higher order function, which is provided by the Kotlin standard library, and it uses regular JVM threads. In turn, the JVM implements threads using general purpose OS threads. They are heavy on resources, unfortunately, so you can have at most a few thousands. This means that they may not be the ideal choice for fine-grained concurrency. So in our application, each thread will retrieve a single information about the stock and will output it on a dedicated result channel. So the average on the average result channel, the current value on the value result channel, and so on. After that, we need to wait for this information before printing it, of course. So we'll join the stock information threads from the main thread by performing a potentially thread blocking receive operation from each result channel. So in this case, we are using the channels as a synchronization mean between the main thread and the information retrieval threads. So after we got the information, we can just, here we are defining immutable values to store them, to bind them, and we can just use their names inside Kotlin string templates, which are very, very pragmatic and convenient. So, well, let's try to see what happens. We can use anything as a stock name because our implementation is quite simple. Okay, so we get the values we asked for. Are there any questions up to this point? Is there anything? Or maybe I can just go on. So, well, anytime you have some questions about specific points, just ask me and we'll talk about it. So, okay, that's fine. I'd like now to jump to a different version of the application, a version that is going to use fibers. So that's it. Let's check it out. And why are we doing this? Well, let's make a thought experiment. So let's suppose that our stock information is coming from a far and slow system, an external system, and we are going to simulate this slow system with threads that will wait up to 3 seconds before returning the stock information, right? So, well, it's just a slow external system. We don't want to waste resources by having the threads wait for the values. So we'd like to use something more lightweight. And also, let's suppose that our system is not going to process only one request, only one stock information request, but many of them. Let's suppose it's an online, global business, 24/7 with many users, concurrent users. So we want to be cheap on resources. We want to spare resources as much as possible, and threads are not the right choice in this case. So we want to use something lightweight. Quasar provides us with fibers, which are very lightweight. We can have millions of them. So let's just use those. And well, as you see, the program hasn't changed a lot. We just replaced the thread construct with the fiber construct, which is provided by Quasar as part of its integration library with Kotlin. And well, that's pretty much it. Actually, this program is even simpler than before because fibers can yield a result when joined. So we don't need result channels in this case. Well, I want to show you that actually fibers are just like threads, debugging included. So I'd like to run a debug session in this case. And I'd like to show you some more Kotlin language features in the meanwhile. So we can, well, fibers can return values. In this case, I'm too lazy to declare an identifier for each of the 3 fibers that we're going to spawn concurrently from the fiber that is retrieving the stock. So I just declare a triple. A triple is a Kotlin data class, and I'm storing the fibers inside it. And then from the fiber that is retrieving the stock information, I just join the stock information the 3 stock information retrieval fibers with the get method, and I include another triple, which I'm going to return to the main thread. So you see, in this case, we are letting the main thread and the lookup fiber interoperate and synchronize through the fiber's return value. They are just 2 different type of strands, but still strands. So this is the important thing. Triple and pair are data classes, so they have all data classes features, plus they have a few convenient properties. But all data classes in Kotlin, they can be structured through multiple assignments, and they have also component methods, so component 1, component 2, and whatever to access their properties. So let's now have a look here. Of course, we can always use whatever stock name you want. Right. Okay. So in this case, you see, we have stopped in debugging. We are inside the stock retrieval fiber, and well, you can see I'm using a normal debugger, normal imperative debugging tools. I can go back I can navigate to the stack, the top frame, the bottom frames. Each fiber has, when running, has an active thread stack. So you can just use normal debugging tools with fibers, just as you will do with threads. In this case, I'm inside the Quasar Kotlin library. I'm looking at the fiber construct, which mirrors the thread one. So well, that's it. You don't need to do anything different that you will do with threads. So let's just go on. Of course, we pass several times through these, and we'll finish. Before going on, well, you see, okay, this is the output. So we have the fibers. They start. They get the values, and we print the values. So it works exactly like with threads, even shorter. I'd like to show you just one more Kotlin feature, which is extension functions. So extension functions, they allow adding functionality to classes whose source are not strictly under our control. So we consider them libraries. We can add features to libraries. They are statically dispatched, so they take into account only the static type. And in this case, well, what are we doing here? We are taking a completion stage, which is the return type of our slow and fast system. And it represents an asynchronous slow computation that is going to end at some point. It is a Java 8 class. And we are converting it into a fiber blocking operation so that we can return to a more traditional blocking, but still very efficient because it's using fibers programming model. And we can do this very, very quickly, very simply through the async completion stage class of Quasar. Right, so, okay, so, well, I'd like now to jump, okay, are there any questions up to this point, or can I just go on?
Hi, Fabio. I think most questions are being handled right now, so maybe we can come back to them later, so please continue.
Okay, right, so I'd like to show you some other features of the Quasar channels. Well, we're going to use channel selection. So now let's think about improving further our application. And what we would like to do is we'd like to avoid our user waiting for all the values being received before being able to see them. So as soon as a value arrives, we'd like to print it to the user. We can do this in several. We can use several approaches really, but this approach is very nice. I think it's very cheap on resources, so we can fetch the results as soon as they are available on any channel by using what is called channel selection. So the select call will unblock as soon as one of the channel operation completes or on timeout. So in this case, we are iterating 3 times. This is a static range. And anyway, we are back to using channels, of course. So the fibers will get their information, and they will output on 3 result channels, like in the first version of our application. And we're going to select on these channels. So we'll wait for 60 seconds for any of these 3 receives to become ready. And well, they are receives from the 3 result channels on which the fibers are going to write. So, and we are performing this from the main thread. So again, we are still synchronizing the main thread with fibers. Okay, so how are we going to understand what happened? So which operation has completed? We can use Kotlin's when construct, which is a very simplified and very compact pattern matching construct. Each branch of the when construct can match a single expression against another expression, against a set of expressions, a dynamic range, or a type. In this case, we are matching against types. You can even use it without an expression argument, so without this part in this case. And it can also replace, because it can also replace the if, else chain with something that maybe is more compact. So, well, all these features make when just ideal when processing the result of receive and select calls. So in this case, well, we have two cases. Either some receive operation has completed or something else happened, which means we got a timeout, right? So, well, if the receive operation has completed, well, we don't need to worry about the type anymore. In this block, we can be sure that the IT identifier has received type. So Kotlin will smart cast it to the receive type so that we can access its features like receive port without doing further downcasts, which is very repetitive and a bit useless. So in this case, if the receive port is the average value receive port, it means that we are getting the historical average. If it's the current value return channel, it means we got the current value and we print it immediately without waiting, and that's it, right? So as soon as some value becomes available, we just select it and we print it. And this is going to give more reactivity towards the user to our application. All right, so let's try it out. As usual, we can use whatever. Quasar, the stock name. Let's see what happens. Okay, so here you see the 3 fibers get started. One fiber got the average, and the average is selected and printed. Another one got the value from the system that is waiting random amount of time, and so we print the value. And we got the advice, so we print the advice as well, right? So this is more reactive. This is a nice feature, very cheap and very clever. Okay, so I'll go on. Now, I'd like to show you a completely different approach. Quasar also offers actors, and Quasar actors are really very much like Erlang actors. They are, I would say, almost identical in every respect. So let's check out this version of the application. Well, actors have been made popular by Erlang to write fault-tolerant applications. Actors are a big topic, really. It's a very sophisticated model, has a lot of pieces, so there's no time for me to cover it all here. So we'll just see how to write one Quasar actor. And a Quasar Kotlin actor, it is just an Erlang actor, so basically a sequential process that will run on a new fiber by default. But of course, you can use Quasar to run it on any strand, so even regular threads. And well, spawned actors, they offer a public handle or reference, and that can be used to send them general or even actor type specific messages if you define it in a proper way. Actor references, of course, they can be passed around, but they can also be stored and retrieved from, of course, a global registry. So this also enables, for example, remoting. Actors have only one input channel, which is their mailbox, but they can perform selective receive operations on the mailbox. So this means that they are not completely at the mercy of the order of arrival of messages, but they can choose to defer some messages and to process others. Erlang has this feature. There are other frameworks that don't have it. Typically in frameworks that don't have it, you have to use state machines. It may be what you want, sometimes it may be not what you want. So in Quasar you have an alternative as you have it in Erlang. Also notice that Kotlin allows top-level functions and properties. So if you don't want to use classes in some parts of your program, because they're just not relevant, you can avoid doing so. So in this case, we define a new actor function, top-level function. It will create a new literal object that extends the Quasar Kotlin actor class, and will override the do-run method, which is basically the main actor method, the method run by the sequential process inside the actor. What are we going to do here? Well, we'd like to change our application a bit, and we'd like to defer the advice so that it can be printed last, because it feels strange to print the advice before we have printed the actual stock information. So, well, whatever comes in first, either the average or the value is fine, but we'd like to print the advice last, even if it comes in first, right? So, so we are going to perform 2 receive operations, still with a timeout. Timeout is always a good idea because you know, the system can be down. We don't want to block indefinitely, so it's always a good idea to include a timeout. And when the message comes in, well, if it's a double, it means that we are receiving the historical average. We just print it. If it's a value, it means that we are receiving the current stock value, and we just print it the same. Well, if it's a timeout, well, this shouldn't really happen. So, well, let's just suppose it won't happen. The other possible case is that we are receiving the advice. So if we are receiving the advice, we don't want to print it before the average and the value. So we just defer. We just defer the advice. We leave it in the mailbox. We do processing for advice messages later. And so later when we have finished the first 2 receive operations, so we are sure we have printed the historical average, we have printed the value, and now we are ready to print the advice. So we perform an additional receive operation. We can be sure it's the advice this time. We just print it. And actually here, well, we are done. We don't have much more to do. And well, we could just choose to terminate the actor to exit the do-run method. And Kotlin allows us to do so. In general, Kotlin has very nice control features, and it allows non-local returns. So you can use non-local returns to jump inside flow control constructs, but also inside inline higher order functions like receive, like Quasar Kotlin receive. So we just exit the actor. In this case, we have an additional println, which will never happen. Of course, the Kotlin compiler can't know it because this semantics is very dynamic. But we shouldn't see never printed the string on the standard output. So let's just run it. Well, of course, yes, there is an alternative. If we don't receive the advice, it means that we received something unexpected or a timeout, which shouldn't happen. So once again, okay, the logging. This is the logging of the actor system. SLF4J, so you can plug whatever logging mechanism you want. And okay, so well, the first thing we get is the advice. Then we get, sorry, the average. Then we get the advice, and then we get the value. So the advice comes in second, but we are printing it third because that's what we wanted to do through the selective receive feature. All right.
So we have actually we have a question from the audience. So
yeah.
So someone is asking, so in this case, wouldn't defer count as a receive? So if the sequence is not what you expect, will you get the unexpected output?
Sorry, could you repeat the question?
So the question is, doesn't defer count as a receive? So if the sequence is not double value advice or value double advice, then you will get an unexpected output error.
I got it, thanks. No, defer doesn't count as a receive. Actually, defer leaves the message pushback. Well, you can think that it pushes back the message in the actor mailbox so that, well, it will not process for this receive round. So that's why it works. That's why in the second receive, we get the advice because it's still in the mailbox.
Okay. Yeah, thanks. And can you maybe talk a little bit about the suspendable annotation? So where exactly do we have to use it? And is there some kind of diagnostics that comes into play if we forget to add it to our
Of
code?
course, yes. Yes. The suspendable annotation should be used in to annotate every method that has suspendable calls in it. So every method that can suspend fibers. Well, in this case, for sure, actors can suspend fibers, because typically in actor main you will be performing some send operations, some receive operations. Receive are fiber blocking, so this is for sure a suspendable method, and you should annotate it. Well, actually, there is diagnostics, of course, in Quasar. There is a lot of it. The most simple one is a system property that you can enable to receive notifications about the Quasar runtime when something is not annotated with suspendable. And these diagnostics have been made very precise lately, so they should be able to catch pretty much anything you forget. We really hope, well, starting with Java 9, probably we'll be able to perform automatic instrumentation of the code without requiring suspendable annotations. But this depends on some features we've been talking about with the JDK guys. So, well, yes, we pretty much hope and think that it will be available starting from Java 9.
Thanks. So no more questions. I think we can proceed then.
Okay, right. Okay, I want to show you another couple of things in the main method. Well, this should really be like this. This is actually the recommended. Well, sorry. Actor spawn. So, well, we just construct the actor and we spawn it. We get the actor reference, and the fibers will send their messages over the actor reference. So that's pretty much it. Right. Sorry. That's why I included it in the first place. It is there because well, you should never use the actor implementation. You should always use the actor reference. But in this case, we have to synchronize from the main method, and we have to join the actor. So that, well, we need to join only the actor from the main thread, because it will be the last agent to finish. The fibers will finish before it, because they are providing values to it. We have to do this because if we don't join, our program's main thread will terminate before the actor has finished executing. So this is actually important. Okay, I think we still have some time. So I'd like to go on and show you another programming style that Quasar supports, which is Dataflow. So let's make another jump. So that Dataflow version of our application. All right. Okay, so, well, what is Dataflow in the first place? With Dataflow, we're actually building a network of computations with a single output each, or of course, they can terminate with an error. And Dataflow nodes, they can be write ones or always mutable. So depending on whether you want to reuse your Dataflow network or not, you have two options here. So you can think of a Dataflow program as a kind of concurrent spreadsheet. And, well, the network arcs are the value dependencies between the nodes, because some nodes, they can block waiting for the output of preceding nodes before proceeding. Of course, well, Quasar will take care of implementing the dependencies between the Dataflow network nodes in the most concurrent way possible. And by default, it will use fibers. So let's come back to our program here. In this case, we have one initial and inert node. I say it is inert because you see there's no computation associated to it, and actually its value will be provided by the main thread. So then we have a middle node that will read from the initial node. The initial node will be provided with a stock name. The middle node will look up the stock and we're doing this actually here. I'm including a lot of printouts, but later I will show you that this notation is really very, very, very compact. And so we are getting the stock. And finally, we are returning the stock as an output of this middle node. And then we have 3 final nodes that are reading from the middle node. Each of them will output a single stock information. So they will get the stock value. They will perform, they will search for the information they have to provide, and they will return it. Now, well, there is a lot of printout just to show how things are working. Later on, I'll remove it, and you'll be amazed by how compact this style can be. And so in the main thread, what are we going to do? We're just kicking off the network by providing the stock name to the initial node. And then we'll join on the final node's outputs so that we can print the stock information. So we just get their values, right? So let's have a run of this. In the meanwhile, well, maybe I'll wait just a bit. So you see, this is a kind of we are really building a value flow or data flow in our program. So it's a very compact style, and Quasar offers you this abstraction as well. So you can choose whatever you feel is best for your domain, actually. So in this case, well, of course, let's use the name of our beloved language. Okay, you see a lot of printouts here. The data flow nodes are getting first the stock name. The other ones are waiting for the stock. The stock is found. So here where the stock is found, and data flow, then the other data flow values, the final ones, they get the value, advice, the average, they return them, and they get printed out. So, okay, so this works perfectly fine too. Another couple of things I'd like to mention here. Well, first of all, let's remove a few printouts. They are very, they make the program much longer than it can be. So, well, you see, this is one-liner. This is a one-liner. This is how we can retrieve stock information and provide it as an output of a data flow network node. By the way, this suspendable callable construction, this is really a functional interface. Kotlin has interoperability with the functional interfaces from Java 8. The type infer is not yet able to remove this annotation, I think, but it's something that will go away in the future. So what you'll see is this, actually, which is very, very compact. All right. So are there any questions about this part or the previous ones? If not, I will just go on. Well, from my point of view, that's pretty much it. I'd like to mention a few more things because I must tell that there is much more to Quasar. So we've just actually scratched the surface. You have seen that all of Quasar concepts, they interoperate very nicely. So we've been using fibers with threads, with channels, with vectors, all together. But we've just used some bits of the actors. And for example, we haven't seen the actors registry, monitoring and supervision, the behaviors, the fact that you can actually hot swap actors code because of their fault tolerance features. And well, this is also a benefit because Quasar is just a library. It doesn't force you into a different programming model if you don't want to, because fibers are just like threads. Even if you choose to use actors, for example, you can just use the bits you want. So it's very easy on you. And we also strive to, we make a serious effort all the time to keep the API lean and clean so that you can learn it and use it easily and actually just the bits you want. Also, Quasar is very interoperable with other technologies too. So for example, Quasar has support for reactive streams. So you can you can easily interoperate with the technologies that use synchronous channels, and you can find all this information, of course, in the documentation, which is very comprehensive. It has a lot of examples, even about how to build projects using different build tools. So, for example, well, you can interoperate with the frameworks like XJava or XStreams or Pivotal Reactor. And for the Clojure people out there, there is Pulsar. Pulsar is Quasar's Clojure personality. It offers an idiomatic API, idiomatic Clojure API. For Quasar, it's I like Clojure a lot, myself, so I'm really a big fan of Pulsar. And it also has a more efficient and full-blown core async implementation that is based on fibers. And you can also get an automatic instrumentation mode, so you don't have to necessarily annotate everything in Clojure. You can just turn on the auto instrumentation mode and go on. Then I would like to mention also Comsat. So you don't even have to give up your set of Quasar integrations. Well, your set of APIs using your application, sorry. So there is a set of ready-made Quasar integrations with the most standard, popular, and cool technologies you want to use. So, for example, you can integrate Quasar with Servlet, Spring, JX, RS, Apache HTTP client, JDBC, JOQ, JDBI, whatever, even Clojure Ring, okay, HTTP, and you will run these frameworks on fibers rather than threads. So you can still use your thread blocking APIs without practically any change, but you can run them on fibers rather than threads. So you will get at near zero cost much more efficiency. Well, if you want, Comsat also has a new API. So if you want to do web development with Comsat, you can use web actors, and you can also choose the backend, because you can choose to deploy on a servlet, on Nethy, on Undertow, and you can write very nice web applications for traditional web HTTP requests or WebSockets or server-sent events. Don't forget about the blog too. It's really filled with a lot of good stuff of several kinds. There are tutorials, there are webcasts, there are more vertical articles, comparisons. I'd like to stress once again that all of this is 100% open source. And also don't forget the forums. So we're really looking forward to having you join the community through the forums or even through the GitHub repositories. So, well, the Quasar one, Pulsar one, yeah. Are there any questions?
There was a question from Anton regarding the data flow. So the question is, how does Quasar manage dependencies between data flow vars to know when to kick off the other 3 data flow blocks?
Yeah, right. Yes. Well, it is just kind of natural for Quasar because, well, each data flow variable is implemented by, well, Quasar will implement its computation with a fiber. So the dependency happens when you try to get the value of a data flow. In this case, you are getting actually the output of the computation of that data flow node, like in this case, stock name val.get, right? So you are blocking on the result of the agent that is performing the computation for that data flow node. In this case, well, by default, it's a fiber. So this is how you depend on other nodes. You just ask for their output, and after that, you just proceed with your computation. Of course, you can depend on many data flow variables. You can depend dynamically. You can use whatever construct you wish, and it will just work. Is that okay? Does that answer the question? Is my understanding correct? Okay. Okay, I'd like to mention one last thing. So I hope you'll be writing very nice Quasar applications. And if you're looking for something to deploy Quasar applications, well, look no further because there is Capsule. Capsule had just been released in its 1.0 version, well, a few days ago actually, and it solves all the problems of fact jars. So, well, it's not just good for Quasar, actually. I think once you try it out, you'll end up using it for pretty much anything that is JVM related, so not just Quasar applications. Okay, so that's all. Are there any more questions?
I just wanted to say thanks to Fabio for a very interesting presentation, and thanks for sharing the details of how to use Quasar with Kotlin.
Thanks to you for organizing this session, really.
Before we wrap up, I would also like to thank you and Parallel Universe for doing this webinar with us and to share a few more links with everybody here. You can send feedback on this webinar to Tudone and RJ Demmer on Twitter. Also, any questions are welcome. You can follow up with us if you still have more questions at robert.demmer@jetbrains.com. And for Kotlin and Quasar information, you can learn more about Kotlin at kotlinlang.org, Quasar paralleluniverse.co/Quasar, and you can follow both of them on Twitter at Kotlin and at puniverseco. So thank you again. Thank you again, Fabio, for joining us in Parallel Universe. And
thanks everybody. And so on my side, I'd like to wish you to enjoy using Quasar with the Kotlin and IDEA, which is, by the way, my favorite IDE, but I think there are many like me. And I hope you enjoy it, and that we'll meet again soon.